So we're in the section of doing integration by partial fraction decomposition, which means we're taking a single ratio like this integrand here, and we're decomposing it, breaking it down essentially into the sum or the difference of partial fractions. Whether it's one partial fraction or two partial fractions, there could be more than one. Okay, so in order for that to work, though, the degree of the numerator has to be smaller than the degree of the denominator. So the overriding strategy that you would use if you saw this problem would be to realize that the top is greater than or equal to the degree of the denominator, and long division trumps all the other methods. Okay, so let's do it. Yeah, he's got 3 in a row now. All right, Rubio passed Cruz, though, in Nevada. So who knows? Who knows what's going to happen? All right, so when we do long division, you want to write them in a descending order. And x squared goes into 3x to the 4th how many times? That is, what is 3x to the 4th divided by 1x squared? 3x squared. Good. And you'll know it's right because when you multiply from on high, you should get the first term to be spot on, and it is. And then we multiply and we get minus 3x squared. We then subtract. So that'll be a minus, that'll be a plus. And remember, we can only add like terms. So I get a 0 in the first term. 1 plus 3x squared, those aren't like terms. So I'm left with 3x squared plus 1. And then I repeat the process. Does x squared go into 3x squared? It does. How many times? 3 times, right? Because that's really 3x squared divided by 1x squared, which is 3. When you distribute from up top, you get 3x squared minus 3. You subtract, which means you change both signs, and you get a 0. And now you can add the 2 like terms that are there. You get plus 4. Does x squared go into 4? No. Okay? So what we do then is we rewrite the integral as the quotient, 3x squared plus 3, plus any remainder, which is 4, over the original divisor, x squared minus 1. So it's just another way to write that rational function. Now, what that does is that already kind of decomposes it into 3 terms, but notice the first 2 terms are just power rule. We know how to evaluate those. So here's where you have to be careful with your notation. If you want to go ahead and find the antiderivative of those 2 terms, you can do that, or you can just wait to do it until the very end. It's entirely up to you. What I'm going to focus on, though, is the third factor, or the third term, and it's not one that I know how to work with. It's x squared minus 1, and the derivative of that is 2x. So we don't generate the x in the top. X squared minus 1 is not linear, so it's not a good candidate for U sub. If it were x squared plus 1, we'd have it, right? It'd be what? Arctangent, but it's x squared minus 1. So in this case, I'm going to go ahead and just integrate everything at one time. Leave the 4 there if you want. And I know that I can factor it. I don't know if factoring is going to help, but I know that it's something I can do. And now you're like, hey, I just factored the denominator into the product of 2 non-repeating, both factors are to the first power, linear, both x's are to the first power, factors, non-repeating linear factors, which means I can decompose that into the sum or difference of 2 partial fractions by using the Oliver Heaviside cover-up method. All right? So it's only going to be on that third term. So again, I'm just kind of bringing around these other guys who are just spectators at the moment. And then the 4, you can decide how you want to deal with it. You can either pull it out front and let it go along for the ride, or you can leave it in the numerator and have it become part of your analysis when you find your coefficients. I'm going to go ahead and leave the 4 there. What's going to happen, though, is I'm going to create a separate term for each non-repeating linear factor. I'm going to leave the numerators blank, and I'm going to leave the sign in between them blank, because that's going to be determined by what I plug in. So if I choose to embrace the 4, which I am, he'll become part of my calculation. So let's come back up to the line where I've highlighted him and look at the first factor, x minus 1. What value of x makes that 0 when you plug it in? 1. Cover up the 1, plug in a 1 to what's left, and you get 4 over what? 2. What's 4 over 2? 2. So that 2 becomes the numerator for the factor that I covered up in the term below, which is 2. And then I do the same thing. A negative 1 makes that factor 0. Cover it up, plug in a negative 1 into what's left, and you get 4 over negative 2, which is negative 2. So I can bring the negative out front and put the 2 up here. And now you've decomposed it into the difference of 2 partial fractions. Pretty nifty. And now we have 4 terms, and all of them are like a Crunchwrap Supreme. They're all good to go. So let's do it. We'll get rid of the integral and the dx. What does 3x squared become? X cubed. And 3 becomes 3x. Now the 2 goes along for the ride. Both of your inside functions in these last 2 terms are linear, so their derivatives of the inside functions are going to be constants. And in this case, both of them generate a 1, which is nice because there's no extra correction to make. So it's going to be 2 times natural log of the absolute value of x minus 1 minus 2 times the natural log of the absolute value of x plus 1. And then, of course, we finish it off with plus c. So again, I would recommend just bringing every term along for the ride until you're ready to integrate the whole thing. Just a little bit easier notationally. Now, let's say that that is a multiple choice question. I doubt that that would be an answer choice because there's logs in it, and we know College Board loves to play with logs. So let's think about what we could do. Of course, that 2 could be brought up as an exponent, right? And I'm going to write it below here, but I'm not going to keep it. I could call that the natural log of x minus 1 squared. The benefit to doing that is would I need the absolute values anymore? No, because it's going to be positive. So that's one option. But here's another option that would probably be utilized here simply because the coefficients of both logs are the same number. So if we factor out the 2 from those last 2 terms, I get the natural log of the absolute value of x minus 1 minus the natural log of the absolute value of x plus 1. So when those coefficients are the same, this is what typically is going to be done. We factor out the 2, and that allows us to condense those 2 logs. Okay, so we have a difference of 2 logs, which means it can condense down to the natural log of the quotient of the arguments. Okay, so it's going to be the absolute value of. The positive terms argument, remember, goes in the numerator. Oh, it's not. I meant to put like a plus sign there, but that's not. Here, let's just fill the space. It's 2 times natural log of x minus 1 over x plus 1, and then plus c. There you go, condensed. They like to do that. Now, we didn't get the chance to do that in the problem above because the coefficients of the logs, if you look up there, they were different. Bless you. We had a negative 1 and a positive 2. But when they're the same, look to do that. Look to condense. And because one was positive, one was negative, it condensed to the quotient. Okay, so partial fraction decomposition by Oliver Heaviside cover-up method. Okay, cool. Very easy to do. Back to logistic growth. All right, so kind of returning to what we were trying to do in the beginning. We were trying to solve this differential equation, right? This is where the rate of change of y with respect to time is directly proportional to y itself, which would be purely exponential, but also jointly to the difference of y from the carrying capacity, the upper limit to growth, which we call L. All right, so let's go back to where we were earlier when we were trying to solve it. We separated the variables already, so we multiplied both sides by dt. So we got k dt, and we divided both sides by the factors y and L minus y, and we had 1 over y times L minus y. So that would be the separation. Now we integrate both sides. This is where we got stuck on the left-hand side. But now we are no longer stuck, are we? Because we have partial fraction decomposition by the Oliver Heaviside cover-up method. We have 2 non-repeating linear factors. So here's what we're going to do. We're going to give each factor its own term. Now on the right-hand side, if you want to go ahead and integrate because it's on its own separate side of the equation, you can call it kt plus c. That's fine. Get that one out of the way. A little bit less writing, or actually maybe more writing, but it's done. Okay, so we do the same thing we did up above. we go to the factored version, and we say, what value, when you plug it in for y, will give you a 0? And the answer is 0. And then you cover it up, and you plug in a 0 for any y's that remain, and you get 1 over L. Remember, L is a constant, so 1 over L is the fantastic new coefficient of 1 over y. It's the numerator. And then we do the same thing over here. What, when you plug in for L into the second factor, gives you a 0? L, right? Because when you plug in an L for y, you get L minus L, that's 0. So cover it up and plug in an L to any y that remains, and you get 1 over L. So plus 1 over L. Nice. Now remember, L is a constant, so 1 over L is a constant. So you could actually pull 1 over L out front and say it's 1 over y plus 1 over L minus y dy. And that equals KT plus C. Sounds like it could be a band, KT plus C. Like KC and the Sunshine Band. No, that's a little longer. Never mind. Okay, so here we go. 1 over L goes along for the ride. What is the antiderivative of 1 over y with respect to y? Natural log? Absolute value y. Cool. Plus, what's the antiderivative of 1 over L minus y with respect to y? Good. Minus the natural log of the absolute value of L minus y. We have a negative correction in there because the y term is second, and it generates a -1 derivative, so we have the correction of -1. Again, we don't need the plus c on that side because we're collecting everything on the right-hand side. So the integral now goes away, and now it's all about doing what? Solving for y. Oh boy, that looks fun. Okay, let's solve for y. What can we do first? Multiply both sides by L. Now, while I do that, so I don't have to do too much writing, I'm going to condense that. You see we can condense that like we just did previously? That's going to be the natural log of the absolute value of y over L minus y. And if I multiply both sides by L, I get LKT plus what's L times C? C. In the process of solving for y, remember, C becomes ShamWow C. So it can absorb unknown constants that are added, subtracted, multiplied, divided, raised to its power, whatever. But once you solve for y and you're trying to find C, now it's locked in. You can't let it absorb anything. Okay, cool. How do we unnatural log it? E it. So we're going to have the absolute value of y over L minus C, or L minus y, sorry, equals E to the LKT plus C. Well, we know what to do next. We've seen this enough, right? We can call E to the LKT plus C, we can call it E to the LKT times E to the C, and E to the C becomes new and improved C, the factor, not the term in the exponent. New and improved C. You all okay with that step? If you want to throw it here, that's E to the LKT times the E to the C, and of course E to the C is new and improved C. And that enables us to do what on the left side? Drop the absolute values. Good, because the C will absorb the plus or minus. This is looking pretty good. Yay! Oh boy. I have two Y's over there. One's in the top, one's in the bottom. I need one Y. How do I do that? Pretend like the other one doesn't exist. Conjugate. Where? On the left? Like L plus Y over L plus Y? Ooh, that's going to give me L minus Y squared in the denominator. That's going to have Y's and Y squareds. It's just algebra, but it's kind of funky algebra, right? How about clear both sides out? Multiply both sides by the denominator? Will that work? Yeah, it's kind of like a chess game, right? You kind of think a couple moves ahead. If you multiply both sides by L minus Y, you could then distribute the C, E to the LKT to both terms. And that'll give you a Y term on the right, which you could then add to collect it with the Y that's left on the left. And then you have two terms with Y on the left. You could then factor out the Y on the left and divide through by the blob that's left on the left. Well, if nothing else, you just fearlessly explore by doing something. All right, so we're going to multiply both sides by L minus Y. So we get C e to the LKT times the quantity L minus Y. And now I'm going to distribute, and I get Y equals C L E to the LKT. And this is a math class, not a English for misspellers class. Minus YCE to the LKT. Oh boy. All right, so now I have a term with a Y in it, so I'll bring it over to the left side and becomes Y plus YE CELKTMNOP equals CLE to the LKT power. Fun. Now, I'm getting there. I'm getting close. I can factor out a Y, and I get 1 plus CE to the LKT power. And that equals CL to the ELKT power. And then, here I go. Y equals CLE to the LKT power all over 1 plus CE to the LKT power. Did I solve for Y? I sure did. So, let's review. If you ever have dy dt equaling k times y, then the general solution is the sect equation, right? Pretty easy to remember. Y equals sec. But if you ever have dy dt equals k times y times L minus y, it equals y equals that, which is not as easy to remember, huh? I think so. Yeah. I don't even know what I said. Yeah. Okay, cool. Let's see if we can kind of clean this up just a smidgen. A smidgen? How are we going to do that? No. That's no. Here's what I'm going to do first. I'm going to multiply by a clever form of 1. 1 over C times 1 over C. What's that equal to? 1. Okay. Let's see what that does. In the top, what happens with your C's? They divide out, and I'm left with L times e to the LKT. And at the bottom, I'm left with 1 times 1 over C, which is 1 over C, plus now the C's divide out when I distribute to the E to the L to the L to the K to the T power. Man. Okay, I'm still in the process of solving for Y, really. I'm manipulating. So what could I call the reciprocal? Notice what that did, and which is nice, is it put my constant in one location in the problem instead of 2. So what can I call the reciprocal of an unknown constant? An unknown constant. So I get L e to the LKT all over C, new and improved C, plus e to the LKT. That's already looking kind of better. Now I'm going to do something else. I'm going to multiply by another clever form of 1, and it's not 7 over 7. It's going to be e to the negative LKT power over e to the negative LKT power. Yep. Let's see what that does for me. I get y equals, I'm still going to have a fraction. What happens in the numerator? I have e to the LKT times e to the negative LKT. The bases are the same, so I can do what with the exponents? Add them. What is LKT minus LKT? 0. What's e to the 0? 1. So I'm left with L times 1, which is L, which the Super Bowl is afraid of this year. They've been calling it Roman numerals up to 50, and then they're like, oh, people aren't going to get it. Yeah. All right. All over C, if I distribute in the bottom, C times e to the negative LKT plus, what do I get when I multiply those together by adding their exponents? I get plus 1. Oh, I'm liking that. So here we go. Just with a little rearrangement now, I get y equals L over 1 plus C times e to the negative L kt power. And that is the one that I think is pretty easy to memorize. Okay? A lot easier than the other version. Okay, so how can you remember that? Well, it kind of makes a word. That one kind of looks like an I, and if you forget the plus sign, you get this word here, right? You get lice, right, which is not very sanitary, but we've dealt with it in our house quite a bit, elementary school. Yeah, you go to Costco and you buy lots of mayonnaise just so you can make lice sandwiches, right? No, supposedly if you sleep with mayonnaise in your hair, it suffocates the lice. So, it also what? Makes them taste better? Oh, ruins the pillow. Ruins the pillow. Right, you have to put a shower cap on, and then a shower cap over that, and then put like a belt around your head to cinch it off, and then sleep outside with the dog. And then you have fleas, but at least the lice are gone. See? No, mayo, not Miracle Whip. Salad dressing doesn't work. It has to be real Miracle. It is salad dressing. Is it really? Yeah. Sure. Yeah. It's called Miracle Whip salad dressing. You can dress your salad with anything, right? You can put pants on it and call it a dress. All right. Hey, that reminds me of a joke I heard. Every salad is a Caesar salad if you stab it enough times. Sorry, that recorded. All right, so you get lice, which is kind of gross, minus licked, which is kind of gross. Lice minus licked. Ugh, ugh. Yeah, lice minus licked. That's how you're going to remember the general solution. Lice minus licked. Lice minus licked. Now, if you don't remember lice minus licked, here's a visual, right? There's lice, right? Don't let it get on you, okay, unless you like mayonnaise. Lice minus, look, there's the minus sign. Don't let it get on you unless you like being down. And then licked. Ooh, yeah, look at there. That's talent, okay? That's a guy I went to school with. No, that's a cow. No, that's a cow. Yeah. Lice minus licked. There's the imagery that are going to help you remember it, okay? It's gross, but it works. Lice minus licked. So the solution to dy dt equals k times y is the sect equation. And the solution to ky times L minus y is lice minus licked. Okay? Lice minus licked. All right. Example 6. Here's an example. Oh, by the way, it's worth pointing out that this does have that recognizable logistic field that we were used to in pre-cal. But we really didn't know why it looked like that or how it was derived. We certainly do now. And you're not going to be expected to derive this on any kind of test because there's a lot of clever manipulations at the end by multiplying by clever forms of 1. But you do have, and what's nice about this version, is you do have your carrying capacity visible in the numerator. That's what's nice. That is your limit to growth. That's going to be the limit as x goes to, or t goes to infinity. You got to be careful here, though, that in this problem, c is not necessarily your initial value. It's not necessarily your y-intercept like it is for the sect equation. You would have to plug in a 0 for t and see what actual value you get. Okay? So here is an example. Calculator active. The population of Alaska since from, I got to change that. since from 1900 to since from 2000 from since. So over that 100-year period can be modeled by the following logistic equation. Okay. So notice that P of T is measuring people. T is measuring time in years since from 1900. Let's go to the calculator. All right, if you have a calculator, feel free to get it out. If not, feel free to not get it out. I am going to type this equation in. This is going to have more of a pre-cal feel to it, okay? And I'll show you what the calculus of types of questions will be, but I want to kind of review logistic. P is the population T years after 1900, and of course T equals 0 corresponds to 1900. We want to, part A, what is the predicted population of Alaska in the year 2020? Yeah, how are we going to do that? Let's say that this were an actual free response question. On part A, what would you have to show? You want to make sure that you're showing everything that you type into your calculator. Let's go ahead and get it in the calculator first. If you want to use the horizontal division bar, this is a good time. Go to y equals, remember alpha y equals gives you n over d, and you type in the number 895598. And then 1 plus 71.57 e, that's second ln, to the negative 0.0516x. Okay, so that's a math print that looks pretty. Now on your window here, if you're going to graph it, you want to maybe graph it first if you're going to use the equation, because you should see a nice S-curve. 0 corresponds to 1900. Let's go out to maybe at least 2100. So let's go out 200 years, and we'll count by zeros. Y min, I'm going to put like negative 10 so I can see the x-axis. And of course, we know what the y max should be, right? Because the limit as x goes to infinity is 895,598. So let's go up to about 1 million just to have a little bit of buffer above there. And then, of course, we'll turn the y scale to 0. Now, if you hit graph, you should see something that possibly resembles an S-curve. And that's an indication that you've typed it incorrectly. So now you can kind of answer questions with confidence. We haven't done any calculus yet. Okay, so now, what's the predicted population of Alaska in 2020? You would have to show P of what? 2020 is how many years after 1900? 120. That would be all you have to show on your paper on a calculator portion. Now, if your window covers 120, which mine does, you can answer the question by going to the graphing screen, hitting trace, and then just typing in on top of the values that it has the number you're interested in, 120. And what's nice is it gives you a blinking cursor so you know exactly where you're at on the curve. 781217, 781217. Did it say to round to the nearest whole person? No, so we better go ahead and put 0.6, and the units would be Alaskans or people. Yeah. Now, if you didn't want to do it from the graphing screen, you could go to the home screen, and remember, you can recall what's in Y1 by hitting alpha trace. There's your shortcut, and then just opening it up and typing in 120, and then closing it. So that has the advantage of, giving us what? It's more accuracy. So if we had done it strictly from the graphing screen, it only showed 0.6. Guess what would happen if it didn't say to round to the nearest whole person? We would get it wrong. Yeah, so we're going to typically do all of our calculations from the home screen. So 01 or 02 would work, and then Alaskans or people. The other advantage of doing it from the home screen is if I needed to do something with that number, I could just type it in, like divide it by 5, whatever, and I wouldn't have to have intermediate rounding error. Okay, how fast was the population of Alaska changing in 1920? This is a calculator question. How fast was it changing at that moment in time, at 1920, at that moment? Are we looking for the p-value or the what? P prime. So we want P prime of, now 1920 corresponds with what value of T? 20. Do you need to take the derivative by hand and then plug in the 20? No. On a calculator portion, all you have to do is show P prime of 20. And then from the home screen, remember your calculator can compute derivatives. It's math number what? 8. N deriv. Math number 8. Yeah, but it's still in the top 10. All right, so dx, this is the math print, and then you can recall alpha trace, y1, that's where our equation is, and evaluate it in Leibniz form at 20. And you get 1678.6 88.078, and make sure that on any final numeric answer you put units. What would be the units on this number? People per year. Yep. So in 1920, the population of Alaska was increasing by approximately 1,678.078 people per year. Part C. When was Alaska growing the fastest, or the population of Alaska? Well, over the Christmas break, you know. Oh, D. Oh, yeah, 1940, 1999. You want to do that? You got the idea? You would put P prime of what? 40, and then P prime of 99, and then write it down. Yeah, I'm going to skip that. But yeah, you wouldn't want to skip on an actual test, but it's the same idea. You get the idea. Alaska was growing the fastest, the population, and what was the population then? Okay, so any logistic curve, remember, the population is going to be growing the fastest at the inflection value, and the inflection value always occurs where? At L halves, okay, at L halves. So part C, we can go ahead and say that the population is growing the fastest when the population, or you could say P of T if you want, equals 8,95598 divided by 2 people. And we want to know how fast is it growing at that moment. So we do it again from the home screen. We hit math number 8. X. We can recall it if you want. Alpha trace number 1. And then you can actually just type it in right there. 8,95598 divided by 2. Oh, yeah, I didn't find it right. That's not right, because what did I just do? I typed in for my X value what? A Y value. Uh-oh, we better find that value first, right? So notice what I did on my paper. I have now shown the equation that I need to solve. I need to solve that for T. So to do that, we do have to retreat to our graph. And in Y2, I need to graph 8,95598 divided by 2. And when you graph it now, it's going to be a horizontal line, and it should cut right through the inflection value. And, of course, how do you find where they intersect? Second trace, number 5. There's only 2 curves, only 1 intersection, so enter, 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 and there you go. So T equals 82.765 years after 1900. So about 1982, a little more than 3/4 of the way through. So September-ish of 82. Now, did we answer the question? How fast is it growing at that moment? Okay, so here's the important part now. We're starting to use our calculators a bit more. I wrote down that 3 decimal approximation to report the answer, but I don't want to use that 3 decimal approximation in my computation. So if you notice, it has stored it in X. If you hit X equals, that number is right there stored. You want to, I would recommend every time restoring it as something else. Because if you go back to the calculator screen and you solve for something else, it's going to override that and you lost it. So just hit stow as alpha A. And if you store it as A on your calculator, come back over here to your paper and call it A. Assuming that there's not already something called A, like if you're not calling area A, then there's no discrepancy. Call it A. It's a reminder to yourself. Now you could say P prime of A equals. So you have the advantage now of referring to it as A instead of having to write it out. And then on your calculator, this is what you want to do. You want to come back and find the derivative not at the y value, but at the x value, which you could now just hit alpha a. Let me delete all that. Alpha a. And that number makes a little bit more sense. 11553.214. And what would the units be? People per year. So, yes. Yeah. So, around September 1982, the population of Alaska, according to the model, was growing at the fastest rate, which is about 553 people per year. I don't know if the model is accurate or not, but it'd be interesting to know what was going on in Alaska. Was that like the gold rush of 1982 or something like that? I'm not sure. Klondike 2.0 or something? Maybe so. All right, part D. What information does the equation tell us about the population of Alaska in the long run? Well, in the long run, that's a nice way of saying what is the limit as t goes to infinity of P of t. And of course, what's the answer? Alaska has a carrying capacity of 895,598 people. Yeah. Now, is that true or not? I don't know. But what's nice is you could actually collect data like on planet Earth, and you can look at population trends that might have been collected over many, many years, and you can actually fit a curve to that data using regression. They do that in statistics, least squares regression. And based upon that model, you might be able to predict a carrying capacity for planet Earth. And then say, ooh, how close are we to that carrying capacity? That would be an interesting thing to do. Now, could something like Alaska, according to the model, which has a carrying capacity of 895,000, could Alaska actually have more people than that living there? Yes, it could. But according to the model, what's that? Yes, according to the model, if you have y values existing above the carrying capacity, because it does describe the end behavior, if you have values existing above that horizontal asymptote, the model suggests that the population would have to decrease. So it would be kind of a level of homeostasis. Is that right? Homeostasism? Equilibrium. Maybe a better word. And so you could have populations like of wolves in a forest, and in the ecosystem, it could actually fluctuate above and below as it self-corrects, it like overcorrects, and then they kind of rebound. So almost a logistic curve turns into maybe a sinusoidal graph up there near the carrying capacity. So theoretical predictions versus what's actually happening, not necessarily the same, but these things give us models that we can use to predict with confidence. How much confidence? I don't know. 95% confidence interval? 98% confidence interval? That's a whole nother ballgame right there. Okay, so that was a little bit of a pre-cal problem with the calculus twist because we were calculating how fast it was changing. Okay, let's look at example 7. The AP exam loves to ask questions that require you to recognize the parameters of a logistic growth function, either from the equation or from the differential equation. So let's look at example 7. The growth rate of a population P of bears in a newly established wildlife preserve is modeled by the differential equation dp/dt equals 0.008p times 100 minus p, where t is measured in years and p is measured in bears. Now, just looking at that, does that have the logistic differential form to it? Well, let's see. It's dy dt equals k times y times L minus y. You have to memorize that. So it appears that instead of p, we're using y. That looks good. And it looks like our k value is 0.008. Maybe that's the agent bear. Oops. License to maul. And then you have L equaling 100. That'd be funny. That'd be funny. So it does fit our model. Okay? So K is 0.008 and L is 100. All right. So let's look at the questions here. What is the carrying capacity for bears in this wildlife preserve? 100. Yeah. 100 what? Bears. Always put units, no bears. Always put units on your final answer. Yeah. You don't really have to show any work for that, okay, because they gave it to you in that form, so that's good. This is just, do you recognize that it's logistic? What is the bear population when the population is growing the fastest? What is the bear population when the population of bears is growing the fastest? 50. 50 bears. 50 bears. 50 bears. Not as good as the 84 bears. Yeah. Was 84 bears? Was that Super Bowl 20? 85 bears. Super Bowl 20. The refrigerator Perry scored a touchdown. All right. What is the rate of change of the population when the bears is growing the fastest? Well, that's kind of what we just did. What is the rate of change of the population when it's growing the fastest? So we're trying to figure out dp dt when p equals what? 50. Now, up here, we had the solution equation, and I had to set it equal to 50, or whatever it was up there, to find the t value. I don't have the general solution or the particular solution. Do I need it, though, to figure out the rate of change of the bears? No, because I'm given the rate of change equation. All I need to do to figure out how fast the bears population is changing is to know what the population of bears is at any given moment. So part C, we could say dp dt evaluated when p equals 50. Again, that's using Leibniz notation. It would equal 0.008 times 50 times 100 minus 50, which is 50. And of course, you could figure out what that is. Type it into your calculator or leave it like that. And what would the units be? dp dt would be bears per year. So not a difficult question if you understand what the variables are representing, L and K. Okay? Questions on that? That could be like part of a free response question, like 3 parts of it. Not that difficult. All right, example 8. Suppose that a population of whatever you want develops according to the logistical differential equation. Now, notice they told you this one was logistical. That's kind of nice, because notice the differential equation is not quite written in the format we prefer to just snag the values of K and P out of it. But we know it can be written that way because it said it's logistical, where T is measured in weeks. If P of 0 equals 5, that is, if the initial population is 5, what's the limit as T goes to infinity? Well, we're just looking for the what value. Does it matter what the y-intercept is? They're all asking for the limit as T goes to infinity. Does it matter what the initial population is in a logistic model? No, we already saw that they all approach the same value. Whether they start below or whether they start above, they're all going to approach L. So what we need to do is we need to extract L from this form. So let's see. I'm looking for dp dt equals K times P times L minus P. So it helps to write that up there. Instead of Y, I wrote P. I need to somehow manipulate this quadratic, and I need to factor it. So how do you know exactly what to factor out? Well, this is your goal right here. You want that second term to be a minus 1p. And right now, if you look at the p squared, it's minus 0.002 p squared. So guess what we need to factor out to make that a minus 1p? A 002p, right? So if you factor out a 0.002p, you're left with, well, when you factor out your divide out, so it's going to be 0.2. The p divides out from the first term, so it's gone. But you're left with 0.2 over 0.002 minus p. And so from there, this looks like it's your k value, and this looks like it's your L value. Now, I guess on a free response, you can leave it like that. That's numeric, but you'd have to state that. But let's do something with it. What is 0.2 divided by 0.002? If you multiply by 1,000, you get 200 over 2. So it's 100? 100? Yeah. Mm-hmm. So if you want to write it like that, 100p, oops, 0.002p, sorry, times 100 minus p. So there you go. Now you have it in the standard form, and now you can answer the question. What's the limit as t goes to infinity? 100. There are no units here because it didn't tell us. Population units. Yeah. What if the y-intercept was 60? It'd still be 100. What if the population were 120? That's more than 100. It's going to decrease towards 100. Doesn't matter. All right, it says to sketch the solution curves.
Teachers and students, please mark.
All right, let's sketch them. For A,
your TV to channel 4 for the morning announcement. You can also view them online at mbhstv.com.
here's what's important. They give us different y-intercepts for a good reason. If I sketch the solution curve for A, I'm going to draw my L, my limit to growth, up there first. The y-intercept is 5, so that's pretty low. Where is what y value is my inflection point going to occur? At 50, and I'm starting at 5. So will I see the inflection value? Yes, so it's going to increase and just draw it somewhere, and then when you get about halfway, then have it increase the other way. So there's the solution curve for A. For B, very similarly, you got y equals 100 up there. But now you're starting at 60. So 50 is right here. You're starting a little bit above that. Are you going to see the inflection value? No, it's already increasing at a decreasing rate. And then the solution curve for part C, here's y equals 100. You're way up there already at 120, so you're above the horizontal asymptote. This population is going to be decreasing, self-correcting towards the carrying capacity. So in part D, then, the last question says which one of the solution curves actually has an inflection point. Our relevant domain is t is greater than 0. Notice it said that up here. The only one that has the inflection value showing is A. Which one has an inflection value? Part A. All right, I've seen questions like that. Again, not that difficult, but it does require a little bit of factoring to get it into the standard differential form. I'm missing a joke. Y'all are giggling. What is it? I have 2 example 8s. Oh, y'all are looking ahead. Oh, example 8. Gosh dang it. I have always been bad with numbers. Since from example 8. There we go. I'm going to keep that. I'm going to call example 8B. Yeah. All right, finishing it up here. The rate at which the flu spreads through a community is modeled by the logistic differential equation, that where T is measured in days. So we had swine 09 here, right, on campus. Swine flu 09. And I wrote a logistic equation that year for the swine flu. It does spread. Communicable diseases do spread according to logistic growth. So this one is actually written in a nice format. It's already in the format we prefer. So it says if P of 0 equals 50, solve for P as a function of T. Uh-oh. Solve for P as a function of T. So that means to find the particular solution, doesn't it? Do we need to show the separation of variables and do all the integration over again? No. The dy dt equals k times y and this one, the logistic, are the two that you can go straight to the general solution. So on part A, we're going to go straight to what? P of t equals lice. And then minus licked. And all we have to do is figure out the L value, the K value, and the C value. And we'll have it. Oh boy, how are we going to do that? Well, don't we already know the K value and the L value? From here, this is the K value and this is the L value. That's pretty nice. So P of t, I know so far, is going to equal 3,000 all over 1 plus C e to the negative 3,000 times 0.001 t. Now, of course, you can simplify that because that's the same as 3,000 divided by 1,000. So you could say P of t equals 3,000 all over 1 plus C e to the negative 3t. But I still need to find C. Now it says P of 0 equals 50. Does that mean that C equals 50? Since that's the y-intercept of the graph? No. I told you that C in the equation is not always the y-intercept. For the second equation it is. But for here it may or may not be. You have to actually plug it in and figure it out. So at 0, 50, at 0, 50, we get 50 equals 3,000 over 1 plus C e to the 0. What's e to the 0? 1. So I have that equation to solve. So to solve that for C, I'm going to multiply both sides by 1 plus C while I divide both sides by 50. In other words, the 1 plus C and the 50 will trade places. Kind of like a double factor swap. Multiply and then divide. So now your trailing zeros divide out over there and you get 1 plus C equals 60 and C equals what? 59. Bless you. So P of t equals 3,000 all over 1 plus 59 e to the negative 3t. And you have now created your logistic model, your particular solution. You didn't have to show the separation of variables. You didn't have to reinvent the wheel for this one. Use your solution to find the size of the population when t equals 2. Okay, so on part B, what would you do? Notation. P of 2 equals 3,000 over 1 plus 59 e to the negative 6. And are there any units? People. Or affluenzins. I don't know if you call them that. I'm going to leave it like that. Use your solution to find the number of days that have occurred when the flu is spreading the fastest. Okay, the flu is spreading the fastest when the population is what? Half of the carrying capacity, which is 1,500. So if you set 1,500 equal to your model, 3,000 over 1 plus 59 e to the negative 3t, could you just stop there and put units on it like we did up above? No, you actually have to solve. So we're going to do the same little trick here. I'm going to multiply both sides by 1 plus 59 e to the negative 3t. And I'm going to divide through by 1,500. Or, well, I got to find, could I use this model up here to find the number of days? That doesn't have t in it, no. So I'm going to have to keep going here. And I'll switch it, and I get 3,000 divided by 1,500. And what is 3,000 divided by 1,500? 2. So now I got to start peeling back the layers. I'll subtract 1 from each side. 2 minus 1 is 1. Divide through by 59, and you get 1/59. Now you have to une both sides, so you natural log it, and you get negative 3t equals the natural log of 1/59. And you divide through by negative 3 or multiply by negative 1/3, and you get negative 1/3, the natural log of 1/59 weeks. Now let's say that this is a multiple choice question. Is it days? Darn it, you don't want to mess up at the end. It is days. Okay. It's spreading faster than I wanted it to. This probably would not be the multiple choice answer, although this type of algebra would be fair game for a non-calculator portion. There's a negative out front, and this is a fraction. So remember, you could do something with the natural log of 1/59. You can either say it's natural log of 59 to the negative first power, right? And then do what with the negative 1? Bring it out front and call it 1/3 natural log of 59. Or you could equivalently say it's negative 1/3 beefy bracket, natural log of 1 minus the natural log of 59. And of course, the natural log of 1 is 0, and the negative times negative becomes positive. So this more than likely would be the answer. But again, it could be the natural log of what? The cube root of 59. I don't think that that would show up. But again, it's an option. No, I'll give y'all an extra day. We've been kind of doing high turnover with worksheets, so we'll make it do Friday. Friday due. But it is all new stuff to everybody, so it's important that you extract as much knowledge from the worksheets as you can. All right, tomorrow we start the next section. On to chapter 6, that's right.